Hi, I'm Jerry Stone. I'm a freelance space presenter, and amongst various things, I have developed this new concept for space habitats, which I'm going to describe today. The story actually goes back over 50 years to Gerard O'Neill, who was a physics professor at Princeton University. And in the new semester in 1969, he posed what was meant to be the first of a number of questions that his students would discuss in order to increase their interest in physics. They never got on to the second question, and it actually occupied O'Neill for the rest of his life. So the question he asked was, is a planetary surface the right place for an expanding technological civilization? And the answer seemed obvious. Yes, you do it on the Earth or else on the Moon or on Mars. But the students went away and they did their research. And the results of that was the answer actually was no, not on a planetary surface. And the main reason was that you will always lose the sun for 50% of the time. Well, on Mars, the day is only just over half an hour longer than on Earth, so that's not too much of a problem. But on the Moon, where the night lasts for 2 Earth weeks, that will mean a major power requirement. The other issue is that on the Moon or Mars, the reduced surface gravity for a permanent settlement is going to mean major medical considerations. So, where should these settlements be built? Well, if that's the Earth and there's the Moon and its orbit around it, if you draw a line between them, you can show some points that Joseph Lagrange worked out back in 1772. So they're known as Lagrange points. So L1 is between the Earth and the Moon, L2 is on the opposite side. Now, normally, a point closer to the Moon will orbit the Earth faster than the Moon, so it will pull ahead. And at L2, you will drop behind. But at these particular locations, the combined gravity will make them orbit the Earth in the same time as the Moon. So they will stay in the same relative positions. There's also L3 over the other side, which is not a lot of use. But these 3 points are unstable. If you move away, you will continue to move away. So anything in these positions will need fuel for station keeping. So L2, which is the location of the James Webb Space Telescope, so that needs fuel for station keeping, and as such, it only has a limited lifetime. But there are also two other points. L4, 60 degrees ahead of the Moon, and L5, 60 degrees behind it, and these are stable. Around those points, if you move away, the combined gravity will pull you back, so you don't need fuel. So designs were drawn up for large-scale space habitats at these locations. And the most practical shapes were the torus, sphere, and a cylinder. So I'm going to show you some designs based on those. So O'Neill's first paper was published in September 1974 in Physics Today, and he showed the practicality of space colonization, which was then expanded in his book, The High Frontier. I actually met O'Neill in 1979 when he came to give a presentation in the UK, and I still have my copy of the High Frontier, which he personally signed. So this was to have a population of 10,000 people. So here are some Italian towns with a similar sized population. So this is a painting done 50 years ago showing an island one habitat. The habitat itself is the sphere in the center. On each side of it are mirrors and a ring of mirrors which reflects the sunlight to the rear and the front mirror, which then bounces the sunlight through ring windows to the inside. The collection of rings in front and behind the sphere are for agriculture, and at the very end, front and back, are manufacturing and processing facilities, plus those large radiators to get rid of waste heat. So if you look through one of the ring windows, you can see the inside, and it is an inside-out world. So we would have a town with villages very much like on Earth, except, of course, the horizon curves upwards. We would take Earth plants and trees. We would take some Earth animals, but we would leave mosquitoes behind, and they kill 1 million people on Earth every year. There'll be no tsetse flies, no lice. There'll be no rats, snakes. So we would actually take some species of wasps which would be useful. And we would take bees to make honey. But without mosquitoes, we could have our barbecues in safety, as you can see at the bottom right. In the rings, we'd have agriculture, which would be carried out on various levels. So these show 4 rings which are open to each other. But if you closed off a particular ring, you could have a different climate in that ring compared with the one next door. So you might have a warmer climate so that you could grow rice. Also, there would be no seasons as on Earth. So whereas here we can only grow and reap wheat once a year, on one of these rings we could grow and reap every 3 months, so 4 crops a year. And with 2 rings, with the crops 50% out of cycle, you could have fresh wheat every 6 weeks. And the same goes for other things. You could have fresh strawberries all the year round. Now this painting shows cattle in the lower section, and now we know we probably wouldn't have cattle there because we'd produce the meat artificially. But we might have dairy cows to provide milk, and perhaps sheep for wool, chickens for eggs, and fish as well. So the designs are designated not on their shape, but on their population. So an island 1 design, and this is also an island 1 level, would house 10,000 people. So here the large ring mirror at the top reflects the sunlight to the outer edge of the central hub, which is set also at an angle, and that bounces the sunlight outwards to the inside of the exterior ring. So this is what it could look like. it's quite likely that the buildings would be mostly composed from mooncrete, that is, lunar concrete. Although I have said that the Scandinavian settlers might prefer to wait until we've grown enough trees so that they can build their houses out of wood. So there's another possible view. So then we come to Island 3. These are the big ones. These can house millions of people, and they are large cylinders, shown here as twin cylinders, counter-rotating, so there's no overall torque. You can see that there are large mirrors which bounce the sunlight through the longitudinal windows to the land on the opposite side of the interior. These cylinders are 4 miles in diameter, 20 miles long, and the ring of small cylinders at the end are for their agriculture. So this shows the main construction, and a cutaway really gives you an idea of scale. So on units the size of Island 1 or Island 2, you would need sprinklers. But for Island 3, you would have natural ray clouds at 3,000 feet. And there's all kinds of sports you could do, including mountain climbing. And as the effective gravity becomes lower, the further you travel towards the center line, you can reach the summits without any problem. So here's a view down one of the cylinders. And again, to give you an idea of scale, have a look at the bridge there. But without earthquakes, volcanoes, tsunamis, hurricanes, a pleasant climate, life in one of these units could be much more pleasant than in many places on Earth. So what would they be made of? Well, we wouldn't take the material from Earth. That would be far too expensive. But we know what's obtainable from the moon, thanks to the Apollo program. There's plenty of oxygen for people to breathe, silicon for windows and for fiberglass, iron, aluminium and magnesium for the structure, plus other things like titanium. Just in the Apollo 11 samples, the titanium content was about 5 times the average on Earth. So how would you get the material from the moon to the L5 location? Well, another advantage of the moon is that it has no atmosphere to slow down any craft travelling outwards. And we have the power of the sun, so we could set up an electromagnetic launcher. It was estimated that for the first spherical Island 1 habitat that I showed, that would need 500,000 tons, which sounds a lot, but some calculations I did showed that you'd only need to use an area on the moon 530 meters square and 5 meters deep. And over the timescale of construction, that wouldn't even keep a single bulldozer busy full time. You'd obviously need to get some material from other locations because of the required mineral content. And also, since the original plans were drawn up, we know now that we'd also get material from asteroids. So the electromagnetic launcher, the mass driver, would not be a continuous strip, but a series of electromagnetic units. And they would refine the trajectory as it accelerated. Now, O'Neill deliberately restricted the design of the habitat of the spherical Island 1 in two ways. First, it had to cost no more than the equivalent of Apollo, so nobody could say that we couldn't afford it. And it also had to be restricted to the technology available at the time, so that nobody could say, well, it depends on this and this and this that we haven't invented. Well, about 10 years ago, I thought, well, our technology has improved a great deal since then. We have better materials, we have new alloys, we have new materials which didn't exist back then. Carbon nanotubes, graphene, and so on. And our computer technology is many orders of magnitude beyond what it was back then. And so instead of the planned 2,000 people needed to carry out the construction, I'd be very surprised if we need more than perhaps 250. Robotic technology will do a huge amount of work. So as a result, I thought, well, if we could to do this now, we could do it more effectively and relatively cheaper. So I set up the space project at the British Interplanetary Society, study project Advancing Colony Engineering. Now, I much prefer the word settlement than colony, but I needed that for the acronym. So when we had our first meeting of our volunteers in the team, I put some ideas to them about constructing Island 1. I said, first of all, we need to extract the raw material, then we need to process it, we need to use that material then to manufacture the various components, beams, girders, panels, windows, etc. And then we need to assemble them. But on top of all that, we also need living quarters for the construction team. The other thing is that all space habitat designs, and there are loads of them, they all assume they will rotate to provide 1G. So I asked the team, do we need 1G? What about 0.9, 0.8 or less? There will be less stress on the structure, so less material needed to build it, it'll be cheaper, and less stress on the inhabitants, on their cardiovascular system, their skeletal structure, and their muscles. And so as we have Island 1, 2, and 3 getting bigger and bigger, and this would be a structure much smaller, we call this Island 0. So it will be composed of modular components, somewhat like the International Space Station, except this would only need 3 different types of main components, unlike the ISS. It would rotate to provide simulated gravity. They would grow some of their food on board. There wouldn't be enough room to grow all that they'd need. But there would also be the opportunity to do some prototype manufacturing facilities. And although it would have simulated gravity, at the central hub, you'd be weightless. So if you wanted to do any research that needed weightlessness, you could still do that. So why have simulated gravity? Well, as I said, the cardiovascular system is affected when you're weightless. The blood is pumped differently. The heart doesn't have to act against gravity, and it becomes weaker. Blood flow goes to higher parts of the body, and people going to the ISS, you can see that for the first few days their faces become puffed out, and all because of the change of blood flow. In addition, their muscles weaken because they don't have to push against gravity, and the same applies to their skeletal structure. The result of all this is that on the ISS, people have to do 2 hours of exercise every single day. So in an 8-hour day, that is a quarter of their time is effectively wasted when they could be doing more productive activities. So Island Zero would be made of main units 15 meters long, 4.8 meters in diameter. For comparison, there's the Bigelow B330 module, which was intended to be a fair bit bigger. And Sierra Space are currently producing designs twice the diameter. The reason I originally chose 4.8 meters is because they could be carried in the payload bay of Skylon, which is the single stage to orbit launcher being developed by members of the British Interplanetary Society. And although its payload bay is only 11 meters long, as I said, these are inflatable units, so compressed 2.85 meters long, which means that they not only will they fit in the Skylon payload bay, but theoretically you could have 4. In actual fact, you wouldn't because of the mass payload capacity. However, you could have 4 launched in a Falcon Heavy, which didn't exist at the time that I first drew up this concept. So not only would they fit, but the Falcon Heavy can carry 64 tons to orbit, so it would easily take 4 of these units. So our original idea was the assumption that they would be assembled end to end and form a ring with radius of just over 22.5 meters. However, when I did some calculations on the resultant effective gravity based on the radius and, in the first column, the rotation rate, I found that at 25-meter radius, even at 3 RPM, you'd only get 1/3 of a gravity. You'd have to have 6 RPM to achieve 1G. And at that small radius, that would not be really tolerable. I thought perhaps a radius of 2 RPM might be the maximum, and that would require 225-meter radius. But even a 200-meter radius, a ring of modules would need 84 units, so it would no longer be a low-cost exercise. So how could we reduce the number of modules? And I came up with the idea that instead of having them in a ring like this, we'd rotate them by 90 degrees and increase the tether length to 200 meters. We then add an outer ring so you could travel between outer modules, and they would look like this with a number of floors. Instead of having ladders between them, we'd have a spiral staircase fitted to the inside of the exterior wall. Now, for comparison, this would have a volume of 270 cubic meters, so 2100 for 8 units. And this is the Destiny module, the largest module on the International Space Station, which, as you can see, is smaller. And the total habitable volume on the ISS would only be half of that of Island Zero, even though its cost was a huge amount compared to what Island Zero will be. So we would also need to be able to get from the central hub to the outer modules. And the first thought was that lifts would be too complicated and too expensive. And as a result, I came up with a series of inflatable modules where you could go out to the end, and obviously you'd need others. And this idea, I found out, was actually produced by Herman Nudnung nearly 100 years ago. So this is a marvelous computer animation produced by one of our team. What it doesn't show, though, is the adjustments that I've made to the design since then. So rather than have the modules vertically, they would be horizontal in two levels. This makes much more efficient use of the floor area. And with the connecting units, they look like this. So, as I said, with the 225 meter radius, but at 3 meter radius, you could have 1G with a radius of just 100 meters, which would be a lot easier. And 3 RPM would certainly be tolerable at that size. So instead of being like that, then to scale, it would be this size, and you only need 2 access rings. And from the side, you can see solar panels off the central hub, which the outer parts would counter-rotate, so you could dock spacecraft without having them spin round. But not only that, the great advantage of the Island Zero design is that if you have additional modules closer to the central hub, at 90 meters, you'd have 0.9G, at 80 meters, 0.8G, and you could even have 0.7G at 70 meters. So this would enable us to carry out the required medical research at different gravity levels simultaneously, and no other habitat design allows for this. So I said originally that I thought a lift would be too complicated, but then earlier this year I came up with the design for a simple lift, not an enclosed cabin with ropes, pulleys, but simply using a rack and pinion. So it would look like this and could go up and down from the outer levels to any of the interior ones, and from the central hub to continue to the other side. So it would look like this. And a smaller version, without needing the closer modules, could also be used to send crews to Mars. So they would start off at 1G, but you would slow the rotation down during the journey, so by the time they arrived at Mars, they would already be acclimatized to the 1/3 gravity. So they would not, as NASA had suggested, have to spend 3 days getting acclimatized before being able to go out. An Island Zero unit could also be used to house the crews to build solar power satellites to send power down to the Earth, and to be used for commercial operations, which NASA is very much in favour of. So we can construct it using current technology. Inflatable units have already been launched into space. We would use current boosters, far more effective than those 50 years ago, so launch costs would be very much lower. It would produce simulated gravity, but at different gravity levels, and allow us to carry out the required medical research to determine the best G level for long-term living in space. We can do commercial activities up there and acclimatized crews going to Mars. So there's the design. It needs more work on it, and I have said that really we could do with a phase A feasibility study. I'm talking about a multi-person 6-man effort, perhaps carried out by ESA or NASA. So I put in a grant application to the Royal Astronomical Society for a small-scale study, and I only heard just a couple of days ago that unfortunately it was not one of the many, many, many requests that they received that has been approved. So if anyone can suggest an organisation that might want to take this on, perhaps a university, for a small scale investigation, then please let me know. Meanwhile, I've contacted Curare, who are the US manufacturers of Vectron, which is a fibre stronger than Kevlar, 5 times stronger than steel. And they supply this to a few companies that produce webbing, which is used as layers in inflatable structures. And in my communications with their manager of international marketing, he said that Island Zero is the most efficient 1G space habitat I've ever seen, which is a marvellous statement of support. So we have our title, we have our logo, and I've said that as going into space can help reduce conflict on Earth, so perhaps we could adjust the logo slightly. We also have a statement courtesy of Blade Runner.
On new life awaits you in the off-world colonies. The chance to begin again in a golden land of opportunity and adventure.
So if anyone would like it's actually now a 5-page file about Island Zero, then do please contact me at that address. So I hope you found this interesting, and I'm happy to take any questions. Thank you very much.